Let's go ahead and start talking about our leading and lagging strands. So before we start talking about those, I want to just talk about a couple basic DNA replication things that'll make leading and lagging strands make a little bit more sense, hopefully, when we get there. So first, know that when someone says leading and lagging strands, this means that they're talking about DNA replication. And we know that DNA is a double-stranded molecule. And when it undergoes replication, so double-stranded molecule, the strands are going to open up and make a bubble. And within this bubble, you're going to add on a new strand right here. I don't know if you guys can see that. And a new strand down here. Okay. And that means that that is semi-conservative. So the other thing that you really need to know for this is that DNA always replicates in the 5' to 3' direction. And this means that new nucleotides are always going to be added to the 3' end. And this is because of a very important functional group there, the 3' OH. This is the only place that you can add on new nucleotides. So we always have to go from the 5' to the 3' direction whenever we're replicating DNA. And since DNA is anti-parallel, that means that one strand goes 5' to 3', and the other strand would go 3' to 5'. So they're going to go in opposite directions. So whenever DNA is going to be replicating, the new strand has to be anti-parallel to the old strand. And I'm going to demonstrate that really quick right here. So let's say this is my old DNA. If that one is 5' to 3', this one has to be 3' to 5'. And then if both of these split, because we know DNA replicates semi-conservatively, this top one was 5 to 3, the bottom one was 3 to 5. And then our new DNA strand, whenever it gets added on, needs to be anti-parallel. So 3 and then 5, 5 and then 3. So even though looking at the top one, my new strand is going in the 3' to 5' direction, if you were to just read it, keep in mind that doesn't mean it replicates that way. It still replicates 5' to 3'. It always replicates 5' to 3'. It's just written 3' to 5' right now, but it will always replicate 5' to 3'. All right. So replication bubbles. So here's my replication bubble. And on linear DNA and eukaryotes, you're going to have a lot of replication bubbles form. Just because our DNA is so long, if we only had one replication bubble and then waited that to expand all the way down, it'd take forever. So instead we have a bubble here, 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 and here, and the bubble just expands until it meets the other bubble. And at that same time, the other bubble is expanding until it meets all the other bubbles, and it just makes it go a lot faster. And these bubbles will extend in both directions. So if this is my bubble, it's going to expand in both directions. Each side of the bubble is going to be called a replication fork. So I have the bubble, and this side right here, and this side right here would be the fork. So if my hands don't make any sense, let me draw this out for you. So this is what a replication bubble looks like. So there's my little replication bubble. This is my old DNA. If I'm adding on new DNA, that would be like that and there. And my replication fork is going to be these two sides right here. So where we need to keep replicating is my replication fork. Okay. So I'm going to draw the leading and lagging strands, and then I'm going to go through this slide, which basically just has a recap of the information we just did and some important things to note whenever you're solving these. So first I'm going to draw them, and you're always going to start with a replication bubble. So let me draw that out. And keep in mind, whatever I'm drawing right now, this replication bubble, that's old DNA. Now I'm going to go ahead and label the 5' and 3' of my old DNA. It would be given to you. So right now I'm just going to pick a spot and put 5' and put 3' and make the rest of it work out to be anti-parallel. But on an actual exam, you would be given a spot that says 5' or given a spot that says 3', so you can fill the rest in correctly. So I'm going to fill it in like this, keeping my old strands anti-parallel. And then I'm going to notice where the origin of replication is. The origin of replication is a DNA sequence where replication is going to start because certain enzymes and proteins will recognize it. And that is always going to be, oops, you can't really see that purple, in the middle of the replication fork. All right, or sorry, the middle of the replication bubble. So now I'm going to add on what my 3' and 5' of my new strand would be. So looking at this top strand first, it is right now from left to right, 5' to 3'. That means my new strand from left to right needs to be anti-parallel, 3' to 5'. So I'm just going to note what that would be. And then on the bottom one, right now, left to right, it's 3' to 5'. That means my new strand, left to right, is 5' to 3'. And notice how I'm just saying it's 3 to 5 or 5 to 3 in terms of direction, not the way it replicates. Replicates 5' to 3' always, but it might be written 3' to 5'. Okay. The next thing that I'm going to do is just outside of my replication bubble, just draw from 5' to 3', which way I'm going to be replicating. So super, super important note here. This is a mistake that a lot of people make, is that they're not going to write down the 5 and 3 of their new strand, and they'll just look at their old strand. And they'll say like, oh, 5' to 3', I must be replicating in this direction. That is not correct. You can't look at your old strand for replication because we're not replicating on the old strand, we're replicating on the new strand. You have to look from 5' to 3' on your new strand. So on my new strand, 5' to 3' on the top goes like that. And what I would recommend doing is, instead of drawing one giant arrow, is to draw 2 little ones going up to the replication fork and continuing. So overall, my arrow is still going in the same way. I just split it up into 2. And then for my bottom one, if I go 5' to 3', it would need to go in this direction. But again, I'm going to split it up into 2 based on the replication origin of replication. Okay. Once you have this, drawing your leading and lagging strands becomes super easy if you can just remember these rules. 1, the leading strand always goes 5' to 3' into the fork. The lagging strand goes 5' to 3' away from the fork. So keep in mind, both of those are 5' to 3' if it goes into the fork. It is your leading strand. If it goes away from the fork, it's your lagging strand. So I'm going to look at this one right here first, the top left. So that arrow goes 5' to 3' into the fork. That means it's leading. And the way we represent that is just with the continuous line. For my other one on the top right, it goes 5' to 3' away from the fork. So that means that it's moving away from the fork. So let's say that this is where my fork is right now. And this is my DNA polymerase that's adding stuff on. So it's going to move this direction, and it has to go this way. My fork moves back here. My DNA polymerase can only add on to this end. So what it has to do is it jumps, and then it'll expand again. And then my replication fork moves. It has to jump backwards and then expand again and keep going. So what it's going to form are a bunch of little fragments, because it has to go forward, jump back, go forward, jump back, go forward, jump back, go forward, jump back, and so on. And those little fragments are going to be called Okazaki fragments, and that's written out on the next slide. So you just represent that with some little lines. So yeah, that's our top strand. Let's look at our bottom strand now. Going 5' to 3', like always, we have our arrows written out. This bottom left one, the arrow is going away from the fork. That's my lagging strand. That's my Okazaki fragments. On the bottom right, my arrow is going into the fork. That's my leading strand. It's a solid line. So now briefly, let's wrap this up with a couple things that we've talked about. So when we talk about the leading and lagging strands, we're always talking about the new strands. So when we go 5' to 3', make sure you're looking in the direction of the new strand and not the old strand. You're always going to start at that origin of replication in the middle, so always draw that first, and then notice where your arrows are going. And remember that both leading and lagging strands always replicate from 5' to 3'. Everything's always 5' to 3'. The difference between the leading and lagging strands is the direction that they go in. Or, shouldn't say that. They are always going from 5' to 3'. The difference is if they're going into or out of the replication fork. So the leading strand goes 5 to 3 into the replication fork, meaning as my fork continues to open, my leading strand can just continue into it as it opens up. My lagging strand, on the other hand, goes 5' to 3' away from the fork. So as my fork continues to open up, it needs to jump back. And this is going to form Okazaki fragments. All right, and that is the end of the leading and lagging strands. So the next video will be over the elongation stage of bacterial DNA replication.
I hope you found this video really helpful. The concepts and information presented in these videos will be true no matter what genetics class you are taking. However, the concepts presented in this video are referencing material currently covered in Baylor University's coursework. Remember, if you are currently enrolled as a Baylor student, we offer free tutoring services. Our tutoring center is located on the first floor of the Sid Richardson building. You will find all the details you need to know about these services on our website, www.baylor.edu/tutoring. You may schedule a free 30-minute one-on-one tutoring session online through Navigate, or just drop in during our open business hours. For more information about our current services, please visit our website. Thank you.